Headlines claim this tiny chip makes Google's quantum computer 1,000 times better, but that number hides the real story. The bottleneck was never just about raw speed or mystical algorithms. It turns out the physical infrastructure required to package these fragile components is where everything breaks down when you try to scale up. By the end of this video, you will understand why a breakthrough in chip packaging matters more than any new line of code for building a true quantum supercomputer. For years, the narrative around quantum computing has focused on computational power as if it were magic waiting to be unlocked by software alone. We hear about qubits existing in multiple states at once and solving problems impossible for classical machines. But this perspective ignores the crushing weight of physics that engineers face daily. To build a useful system, you must take those delicate superconducting circuits and house them inside a cryostat cooled to near absolute zero while connecting thousands of control wires without introducing heat or signal noise. The current approach treats each quantum chip as a hand-assembled laboratory curiosity rather than a manufacturable industrial component. Consider the sheer volume of wiring required for today's processors. As you scale from hundreds of qubits toward millions, the interconnect density becomes an impossible engineering nightmare using traditional wire bonding methods. Every single control signal needs its own physical path through vacuum chamber feed-throughs to reach the chip inside the dilution refrigerator. You cannot simply add more wires because each one acts as a thermal bridge that leaks heat into the ultra-cold environment where qubits need to operate. That incoming thermal load causes decoherence, meaning your fragile quantum states collapse before any calculation can finish. The signal crosstalk between adjacent wires also becomes so severe that it corrupts the data being processed by neighboring qubits. This is why the specific metric of 1,000 times better performance appears in recent reports from Google quantum AI researchers like John Martinis and his team at RxIve. They are not talking about a software optimization or a faster algorithm running on existing hardware. That number represents a fundamental shift in how we construct the physical system itself. The breakthrough lies in solving the interconnect density bottleneck by moving away from discrete chip packaging toward three-dimensional, integrated quantum supercomputer architectures. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Think of it as the difference between building a house with individual wires running through every wall versus embedding the electrical grid directly into the foundation and walls during construction. In the new approach, we treat the tiny chip not just as a processor, but as a localized processing unit that minimizes wiring complexity by handling control signals closer to where they are needed. This allows us to stack multiple layers of chips vertically rather than spreading them out horizontally across a massive board. The result is a drastic reduction in the number of physical wires required, which directly lowers the thermal load entering the cryostat and eliminates much of the signal interference that plagues current designs. But here is where most explanations stop short. Simply making the chip smaller does not automatically grant you 1,000 times better performance if the underlying error rates remain unchecked. Quantum error correction is the missing piece in this puzzle, and it requires a level of reliability that has never been achieved at scale before. Current benchmarks emphasize that without standardized fault-tolerant protocols, raw qubit counts are meaningless because errors accumulate faster than they can be corrected. The trade-off between physical reliability and theoretical potential means we cannot just miniaturize our way to success. We must solve the physics of error correction simultaneously with the engineering of packaging. The primary failure mode for scaling quantum computers is not merely coherence time, which refers to how long a qubit stays in its superposition state before collapsing due to environmental noise. It is the physical impossibility of routing control signals to millions of qubits through existing vacuum chamber feed-throughs using current manufacturing techniques. You cannot fit enough cables into a standard cryogenic system without it becoming a thermal disaster that destroys the quantum states you are trying to protect. The tiny chip breakthrough represents a fundamental change in cryogenic infrastructure design because it transforms the packaging yield and thermal management of the chip stack from secondary concerns into the primary limiting factors for production. This shift changes everything about how we view the career paths required for this industry. Data engineers who have spent decades optimizing code will find their skills insufficient unless they also master designing what amounts to cryogenic data centers where physical constraints dictate logical architecture. Hardware-software co-design becomes the critical skill for the next decade because you cannot write efficient quantum algorithms if your hardware cannot physically support the necessary qubit density without overheating or introducing errors that make those algorithms useless. The manufacturability of these systems is now the bottleneck, transforming quantum hardware from a lab curiosity into a system where production yields determine whether we ever reach commercial viability. The evidence suggests that while packaging innovation is absolutely required for scalability, the magnitude of performance improvement remains a projection dependent on solving error correction first. We're moving from an era dominated by noisy intermediate-scale quantum devices to one focused on fault-tolerant architectures capable of running complex algorithms reliably. The path from hundreds to millions of qubits requires us to stop treating quantum computers as standalone processors and start viewing them as integrated systems where the packaging, cooling, and control electronics function as a single unified unit. This is why Google's strategic pivot toward quantum error correction aligns so closely with their new packaging techniques. Neither can succeed without the other. When you look at the RxIve research detailing this transition, it becomes clear that we are facing an arduous path from current benchmarks to practical supercomputing power. The 1,000 times better performance claim is not a guarantee of immediate availability, but rather a projection based on solving these intertwined challenges simultaneously. Until we can manufacture chips with high yield rates and integrate them into scalable cryogenic systems without introducing thermal noise, the theoretical potential will remain out of reach for most applications. This reframes the entire narrative from mystical computational power to a tangible systems engineering nightmare that requires precise collaboration between material scientists, electrical engineers, and computer architects. The real breakthrough is not in making qubits faster, but in building the infrastructure they need to exist at scale without collapsing under their own physical weight. That is the story behind the tiny chip, and it explains why this specific innovation matters more than any new algorithm for the future of quantum computing. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.